specific losses in the material or specific adsorptions.
And that just gets into if it has a certain functional group or something like that. No?
Exactly. So the other part of this, and this is something that we didn't talk a lot about in class, but if you plot the loss terms, they occur right at these humps. So this is loss, or the E double prime, the dielectric loss. And those losses now are specific adsorptions, right? So they correspond to points on the UV vis, or points on the IR, or points in the dielectric spectroscopy where you have specific adsorptions. We didn't harp on that in class, so we probably won't test on this loss part. But the adsorptions, the adsorptions that we talk about in the dielectric losses are the same thing. Yeah.
Okay. Can you relate refractive index to like transmission, absorption? I mean, because refractive, doesn't that mean reflecting? Whereas absorption would be how going through, where in actuality that you have things that go through, there's things that are absorbed and things that are bounced off.
Yeah. So refractive index refers always to transmission. If you can't get the light through, it's not going to have a refractive index. So refractive index is not adsorption. It's all transmission. But really, the thing that you want to take from the spectroscopy part is what's adsorption, what's transmission, what do they mean, right? So if I tell you for adsorption, if I send in 300 nanometer, 500 nanometer, 700 nanometer light, and my material has a strong adsorption at 500 nanometers, what type of light is going to come out of the material? 300 and 700. Right? 500 will be absorbed in our material. So I can say that this material has a high adsorption at 500 and a high transmission at 300 and 700. So this doesn't have anything to do with refractive index. Refractive index refers to the polarizability or the dielectric constant, something like that. Adsorption and transmission is just that, adsorption and transmission of the light.
Okay, so we don't not to think of them on the same.
We don't need to think of them as the same, yeah. Yes?
If I asked you to describe the shape of the refractive index against the frequency curve, would we use the, what you just said earlier, at the steps? That's where there's high absorption.
Correct.
That's it?
Yeah. Just what you said. So those steps are where you have high adsorption in your material. So whether you draw the steps or not, it doesn't really matter to me as long as you know the general shape of the curve that's sloping down and why that happens. Why the curve slopes down slows down is the material is able to respond less at high frequency, right? So if refractive index or dielectric constant is the ability of the material to respond to an oscillating field, we know that material will have a lower response at high frequency. It will have more of a response at low frequency, so that's why the curve comes down. Yes?
I have a question about solubility. Is there anything that's like particularly important about it other than that it's proportional to 1 over the dielectric constant?
On solubility, it's important. We went over a couple of examples. Well, yeah, so the most important thing, I think you hit on the most important thing, is that the solubility is inversely proportional to dielectric constant. So as the dielectric constant goes up, the solubility goes up. As the dielectric constant goes down, the solubility tends to go down. You also need to think about the example, especially where we have water versus methane water versus methane interactions. And so we looked at the pairing energy of water versus water. It was something like negative 114 kilojoules per mole. We looked at the pairing energy of methane, and then we looked at the pairing energy of methane and water. And from those, we could figure out that it was unfavorable for water and methane to mix, where it's favorable to have water-water interactions and favorable to have methane-methane. So we went through a very complicated exercise for hexane in water. That's probably not so important, but these pairing energies are important in that one gas phase example. So you won't necessarily have to be able to compute all of those little different properties, but if I tell you about the interaction energies, you should be able to tell me which one's favorable and which one's not. You know, if the delta G is negative, delta G is positive, those are the types of things you need to know about solubility. Yeah?
On the in-class practice, you had listed different molecules, all the carbon centers and 4 around the edges, halogens and hydrogen. You had the carbon kind of 4 bromines being the least volatile.
Yeah.
That confused me because to me it wouldn't have dipole moments, but I know it was the most massive. So please explain that.
Yeah, that's a good question. So it's this one. This one and versus the other one, which was right. Which one is more volatile, right?
Yeah.
Here you have a dipole, right? And here you have no dipole, but you have dispersion forces. And so this problem is not easy to figure out just from inspection. So what you need to know especially is that HCl and HBr, I think there's some analogy that I provided in the annotated answers, right? Where HBr has a much lower boiling point or is much less volatile than chloride because bromine is so big. So the dispersion forces in bromine are huge. And that leads to very high dispersion forces here, or very strong van der Waals interactions here that dominate over the dipole interactions when you have less bromine on. But that one you can't necessarily figure out just from inspection. So on an exam, I probably won't ask you something that's that complicated. However, if I ask you something like methane, yeah. Which one's more volatile?
Methane.
Methane's more volatile. Why?
It has less mass, so it has smaller dispersion forces, so the overall temperature is less.
What's that? Yeah, methane has lower boiling point, means it's more volatile. But yeah, I think you got it just right, is it has lower dispersion forces because it's not as polarizable as CBr4. So it's hard to compare dispersion, if I give you CH2, Cl2, and I say, well, compare these. You're comparing dispersive interactions in CBr4 versus dipolar interactions versus CH2, Cl2. That one's not so easy to do just by inspection. I'll tend to give you things that are pretty much straight up comparison. The easy one to do is water. So which one is more volatile, CH2, Cl2, or water? What would you guess? Yeah. Why?
It's more polarizable.
Well, if I ask you which one is more volatile and you tell me this, right? That's the correct answer. It has a lower boiling point, more volatile. But why?
weaker
Weaker intermolecular interactions because water is special. It's got hydrogen bonding, right? And so this one, I don't know which molecule is more or less polarizable, right? I can only tell you that water has very strong hydrogen bonds that leads to strong intermolecular interactions. So chances are, if you add up the molecular weights of these two, right? Water is 18. What's this one? 70, 85, something like that, right? So you can't necessarily go on the molecular weight because you just told me that this one was more volatile, which is true. And so you need to think about the one special case of water. Now what about, let's see. What about, which one is more volatile? Yeah, why? Weighs less, so you have molecular weight effect. It's probably less polar because you have two chlorines here, right? So you can kind of figure some of these things out on inspection. What about, let's say, and all these are hydrogens. Which one is more volatile?
First one.
Top one, right? Why? Weighs less, right? And it's got
Less intermolecular forces?
lower intermolecular interactions. It's less polarizable. This one's got more electrons around it, right? So you can create bigger dipoles or bigger induced dipoles in this molecule. So I think you guys have a good feel for those comparisons. It's just that was particularly tricky, but it's meant for discussion and to make you think.
So which one will have a higher boiling point? The one who's more polarizable or the one who has more polarity in the molecule?
Well, that's a good question. So what's more polarizable versus what has higher polarity? It's hard to compare